All right. Why don't we go ahead and get started? So today, yeah, right. You can hear from there, right? So today we're going to keep on talking about pulsars, and we have to just think about some of the other things that go along with what happens in terms of interesting phenomena that you get from these rotating neutron stars. Primarily what goes on in terms of creation of this pulsar wind nebula. So last time we were talking about generic properties, and we've already said sort of that the average mass is this 1.4 Kelvin masses, and that the average period, or average size rather, is something like 10 kilometers. And we'll discuss in the toot one way in which we can really estimate what these masses are, how we get at those masses. And here is just a plot showing sort of the variability of that. You can see there's some which are heavier, and you also see a hint at how we're going to figure out the masses because they're all coming from binary systems. All right, so that keep that in mind for when we get over towards the toot part of the course of today. All right. Now, the thing which we mentioned also last time is that a neutron star really has sort of a black body spectrum from the fact that, well, it is an exposed core of a core collapse supernova, which means it was hot. That's certainly going to emit. And so we have a nice sort of thermal spectrum. But we also mentioned this idea of sort of the lighthouse model, getting these beams of from relativistically moving particles spiraling around the field line, emitting radiation, and that gives us this power loss spectrum associated with the synchrotron emission. When we think about these two forms, that certainly sort of seems to account for all the emission directly from the neutron star. And we'll see that this is a quite useful thing to think about because it's going to guide us in towards understanding that there has to be, in fact, a wind also coming off of this star in order to explain sort of the rate at which it spins down. So just a reminder of what we're talking about. We have this pulsar, has some rotation axis misaligned with its magnetic field. The magnetic field lines, some of which are closed, some of which are open, are emanating in mostly this sort of dipole kind of magnetic field, like a regular bar magnet in the end. That's the basic model. Now, why is there this sort of difference between closed and open field lines? Well, because the field lines, remember, want to sort of be as rigid bodies, which means that as we start rotating our neutron star, some of these field lines, farther they extend from the neutron star, if they're closed, are all going to be rotating at this constant sort of rigid body rotation, which means the velocity, the tangential velocity, just goes as the angular velocity times the distance from the star. And you can see that certainly if I just keep allowing that to increase, then I'm going to run into a point where I have this sort of speed of light motion. And in particular, that's sort of really bad kind of thing if you think about the fact that we're saying we have charged particles that are spiraling around these lines and moving with them. Right? We don't necessarily talk about sort of the velocity of a field line, but we can certainly talk about the velocity of that charged particle which is spiraling around the field line being dragged along with it. And we know that particles cannot travel at the speed of light, and certainly not faster. So this light cylinder is a very important feature of the neutron star and defines basically the last region where we find the closed field lines. All right. But the idea here is we have this rotating neutron star with the magnetic field lines misaligned to the magnetic axis, rather misaligned with the rotation axis, which gives us all those nice beamings of the particles But we want to talk a little bit more today about where the particles come from in the first place, and also a little bit more about where the magnetic field comes from. Yet last time we already mentioned one idea, which is just the fact that if you had a magnetic field to begin with, and you let the star collapse, then you're going through flux freezing kind of ideas, immediately conclude that the magnetic field has to get stronger as you collapse the star. But we'll see there's a few additional mechanisms that certainly contribute and actually lead to a different class of object. So again, we had this last time, this lighthouse model, beaming of particles. But the questions we're interested in, where do the charged particles come from? Well, they're actually coming from the surface of the neutron star. How are they being liberated? And what's going on there is something we're going to discuss shortly. And then, once they're liberated, they of course spiral along the field lines and give rise to the synchrotron radiation, which comes out beamed along the direction of motion, gives us these beams which sweep across the sky. And if we happen to be in one of these, in the path of this lighthouse beam, we see the pulsar. So, what do we think is going on? Why are we getting charged particles coming off the surface of this neutron star? Well, certainly part of it will have to do with saying, of course, that we must have some charged particles sitting around. And we'll talk about the structure of a neutron star towards the end of today's lecture. Again, we hinted at that in last week's toot. But we'll see exactly how things are distributed across the neutron star. And we'll see that one of the things we have are ions sitting sort of at the surface. And when we consider that, then we consider also the fact of some basic electrodynamics. And we've said we've got this strong magnetic field, and the thing is rotating, misaligned with the rotation axis. Well, what does that mean? It means that we have this magnetic field, which is rotating, it's changing. And in electrodynamics, you learn that a changing magnetic field does in fact induce some electric field. So, in fact, this magnetic field rotating with some angular velocity omega induces some electric field that goes basically as the magnetic field times that angular velocity. This in turn means there's a potential difference across the neutron star. And we can talk about that as just being on the order of E times R, where E is the electric field that we're inducing, which is basically B omega, and R is the radius of the neutron star. If you substitute in sort of typical values for the rate at which these guys are rotating, typical values for the magnetic field, and that 10-kilometer radius, then you can convince yourself that potential is something like 10 to the 18th volt. Now that's a quite strong potential, and is going to actually result in basically being able to overcome the binding energies and even the gravitational force from this neutron star to free up these ions that are sitting in the surface of the star and give rise to this emission of particles, which can then go ahead and spiral along the field line and give us our synchrotron radiation. In particular, we can go ahead and compute and check that indeed this sort of overcomes the gravitational force, or at least that the magnetic force on these guys is even more significant than the gravitational force once they're liberated. So they'll go ahead and spiral along the field lines, and that'll be sort of the dominant effect. Just by direct computation, well, the force of gravity on some particle is just m times the gravitational acceleration at the surface. Right, that's sort of the largest it's ever going to be. And if you just check that for, say, an electron, well, you find it's 10 to the minus 18 newtons. Right? And that, of course, seems small, but that's, notice the value of G neutron star is something like 10 to the 12 meters per second squared. So we realize the gravity is really strong. It's just that we're considering a single electron, which is why we get this sort of seemingly small force. On the other hand, the magnetic field is going to be the charge, which is the elementary charge, E times the velocity crossed into B. We'll go ahead and sort of consider the maximal case. Say V cross B is just giving V times B, so they're perpendicular. In that case, EVB you can compute using the radius of the neutron star, etc. In that case, what you find is 3 times 10 to the minus 5 newtons. So 13 orders of magnitude larger. Alright? So we can see that indeed once we've liberated these guys, it is the magnetic field which is going to really dominate what happens. Right, so that dominates the particle's distribution. Now, where do we get these strong magnetic fields? So we talked last time about this idea of fossil magnetic field, that, well, I had a star, it had some magnetic field, I did some core collapse through flux freezing kind of ideas, I've compressed all those field lines, which amounts to strengthening of the B field, and then I've got my nice pulsar. And that certainly works, and indeed we could sort of model it and predict that that will give us fields up to sort of 10 to the 15th Gauss in the extreme case. On the other hand, you start thinking, well, where did the magnetic field in the star come from? And the standard model for the magnetic field of the sun and things like that is that there's a dynamo in action. So you might be tempted to then start thinking, well, if the sun and all stars, and in fact even the Earth, we think has a magnetic field due to this dynamo type action, right? Which just means that you have moving charges, and moving charges give rise to magnetic fields. Well, if that's what's going on in all of these objects, why couldn't it happen in a neutron star? We already talked about this idea that it's kind of a superfluid of neutrons, and if there's mixed in protons, as we discussed in the toot, well, then we certainly have moving charges. So if this dynamo exists in a neutron star, in that case we can actually find larger magnetic fields up to 10 to the 16th. And that leads to this prediction of something called a magnetar, which is indeed this sort of other class of neutron stars, which we're going to talk about. There's one last idea of thermoelectric instability. This gives sort of weaker fields of 10 to the 12th Gauss, confined, however, to the outer crust, which makes it really easy to sort of modify. And we don't really think, firstly, that it generates, obviously, magnetar type field strength, but also it's not going to be all that long-lived, because it's really easy to modify it since it's based in the core, in the crust, rather than sort of throughout the neutron star and through its core. Alright, so the fossil field we talked about last time, so I'm not really going to say much about it. It's just this idea, there's a massive star, comes from the dynamo early on, collapse down, compress it, gives us this nice field. Now also, it is worth noting that really some stars have a fossil field rather than a dynamo generated field, and that would suggest either that it's left over from an earlier phase of the star's life when there was sort of a dynamo and it then got flux frozen, or there is in fact a known magnetic field for a galaxy as a whole, and so if you form some stars in that, well, you're being permeated by the galactic magnetic field, you can go ahead and trap those field lines and let them close and form a magnetic field for your star. Then that massive star dies. That certainly gives rise to a fossil magnetic field in the neutron star that you form through the death of that massive star. And the reason that sort of we only talked about that one last time, and why we kind of like that as the generic story of what's going on, is that it has all the right properties. Because a fossil magnetic field then is very stable, which is kind of key if we think about ways in which the pulsar is spinning down, and we know that that rate is very constant, so that it's a very accurate plot. But it's also a very long-lived magnetic field, sort of as a result of that stability. And so that's sort of a perfect candidate, because we understand also that these pulsars are long-lived. We'll talk about the Crab Pulsar, which has been around since 1054 AD. So you know these guys need to live for quite a while. You're going to want a nice, stable, long-lived magnetic field. Now, there's a nice question of why is this 10 to the 12th Gauss the typical magnetic field for pulsars? And the idea of thinking about this dynamo action kind of leads to sort of really asking the question in terms of why is it so low compared to what you would expect if you also had some dynamo action. And in particular, the idea is, well, if this guy is born rotating quickly and it's the superfluid, then rotation of the star as a whole and any convective bubbles will also drag these field lines. Right? And there'll be moving charges creating their own kind of field lines, but also dragging any remnant fossil field lines along. And that will very much ramp up the star's magnetic field. So, if that's the case, then why are these guys so low? Well, the conclusion is almost, right, sort of, it hits you in the face. If you have a low magnetic field, and you say dynamo will give you a high magnetic field, what can you conclude? Yeah, for most of these pulsars, you just don't get this dynamo happening. Alright? And so that will be the conclusion, but let's keep thinking about what would happen if the dynamo worked. If it did work, it could actually give us this 10 to the 16th Gauss magnetic field, which is 10,000 times stronger than what we're finding in pulsars. So people started thinking, well, if this can happen, then you're going to have those magnetar type stars. And in particular, it's worth noting that you get this over a time frame of just 10 or 20 seconds in the star's life, during which you actually have this possible time for convection and dynamo type actions to ramp up the magnetic field. All right, because it cools quite quickly from that hot forming state and gets rid of these kind of convective and dynamo motions. So if we're getting rid of that sort of thing, if we're getting rid of that motion, then of course the action has to cease, and everything else will then just be the result of having frozen into the star. And indeed, it's a very short time frame, but even in that 20 seconds, you can ramp up the fields to 10 to the 16th Gauss. So it's quite an effective mechanism. And then it goes back to sort of the normal story that, well, I've had these field lines, they're now flux frozen into this plasma of the neutron star, into that superfluid, and so it's not going to change. It basically becomes like a fossil field. It will be sort of long-lived, and will have this much stronger field as a result of having had just 20 seconds or so of this dynamo action taking place. Now, as we said, this leads us to suggest that most pulsars have not successfully done any of this dynamo action. But on the other hand, we can think about that something actually does have some dynamo action. Now in particular, we're going to be talking a lot about the Crab Pulsar today, so it's worth noting it's sort of your normal pulsar story. It has a period of 20 milliseconds at birth. That is not fast enough to sustain any kind of dynamo action, which is why it falls into the normal category of pulsars. But on the other hand, it's sort of easily conceivable that if we had a star which was either rotating faster and then collapsed down and therefore was a much faster rotating neutron star, that we could easily reach periods where we can drive that dynamo action. And so that gives us magnetars. All right? And the story there is basically the same idea. You have the core collapse and all of that happening, but this guy is sort of hot enough and rotating fast enough as a result of being more massive core collapse product, which means that in its outer layers, at the very least, it can drive convection in these sort of convective cells, as you see in that sort of cutaway diagram. That convection means we've got moving charges, generates some more magnetic field. That convection also grabs the magnetic field lines which are already there, twists them up, and gives them that extra bit of energy, making them stronger. Okay, so in particular, if you're spinning faster than something like 200 rotations per second or revolutions per second, then the dynamo action can occur and quickly build up this magnetic field. So there's this well-known threshold to where you can get a magnetar. And if you sort of work backwards from the radius of a neutron star, you could relate that, say, to the original condition on the original rate of rotation of that star, right? Just through conservation of angular momentum. Now, that actually amounts to sort of just slightly faster rotation than a typical pulsar, and so it's not too surprising that maybe we actually have this class of objects. One thing which will be interesting about them, however, is that because of this much stronger magnetic field, which we'll sort of talk about today, that's really, and we already talked about it last time too, this idea of flux freezing also suggests that since the magnetic field extends out into regions which are not rotating as fast as the pulsar, that's flux freezing drags the pulsar in some sense and slows down its rotation. Well, if you have a stronger magnetic field, the effectiveness of that drag is increased. So these guys actually spin down much faster than pulsars. That'll be one interesting point. On the other hand, their lighthouse beams are going to be sort of much, much stronger and much more highly concentrated. Why is that? Well, the faster the particles are being sort of moving right along those field lines, the more they directionally focus their beaming of radiation through this relativistic effect. We already said charged particles emit radiation, and the faster they move, they get beamed in the direction of that motion. And so these guys have a stronger magnetic field. You're going to get a stronger emission, stronger focusing of that beam, so you'll have narrow pulses, which are, in some sense, brighter. So then it will quickly do that, and then these beams become, in the end, narrow. The magnetar beams are these narrow beams, which are brighter. But then, as you sort of spin really slowly, you kind of start to lose that, and you can even, in some sense, turn off the beams. So here's a sort of comparison of what the properties are. The initial rotation for the magnetar is really fast, but it spins down fast as well. The energy of a magnetar really comes from the magnetic field, because it is now so much stronger than what is found in a pulsar. While a pulsar, though it has a fairly strong magnetic field, is still really rotationally powered. The field strength, typical ranges are given there. For a pulsar, actually is in this range, 10 to 11, 10 to 12. And then for the magnetar, 10 to 14, 10 to the 15. And so the spin period is going to be long for this magnetar, because it's actually gone through the process of a rapid spin down from its initial formation. So they're now observed right after formation with a long period, compared to pulsars, which have a short period, which also sort of plays with the characteristic age. The characteristic age for a pulsar will be old in general, while the characteristic age will be young for a magnetar, and the pulse shape, broad for a pulsar, narrow for a magnetar. And here is just a schematic diagram kind of representing the fact that they basically start the same, just have a star, undergo core collapse supernova, and then it's just a question of what's going on with the rotation rate of the neutron star that you formed. If you're kind of slow, you end up with a pulsar. This is a story we went through last time. And if you're kind of fast, you end up with this magnetar, which is a story we've just gone through. That if you're rotating fast enough, generate an intense magnetic field from convection and the fact that you are grabbing all the existing field lines and twisting them and contorting them, then the magnetar settles down as age goes on. It emits a narrow possible beam or a completely turned off one, depending on how much is going on in terms of that beaming and that slowing down of the rate of rotation. And then the old magnetar finally cools down, and it's now rotating much slower because that change in its rotation rate was much faster through that stronger magnetic field. And as a result of having slowed down and having had that magnetic field kind of come from really these convective things in the surface, much of that has decayed away. So we turn off the beam, we slow down rotation, and it emits very little energy in the end. Now, there's a sort of interesting phenomenon that's worth mentioning while talking about magnetars, which is the fact that magnetars can have bursts of emission. The magnetic field in the star is still kind of strong. We have this very strong field permeating regions of the crust. Now we imagine that the crust of the star should be kind of rigid and solid, but because this magnetic field is sort of cutting through it, that can actually result in breaking up of the crust, crumbling of the crust, and that releases a huge surge of energy. Basically, as sort of the magnetic field was twisted up and it's trying to realign, and so you get this breaking of the crust, which emits some energy. That star quake causes this surge in electric current as the crust moves around. That then decays. It leaves behind a sort of hot region on this neutron star, a hot fireball, and that then cools by releasing X-rays from its surface, which takes just time scale of minutes or so. And so you get these bursts of energy of X-rays coming off of the magnetar. And this starquake idea is sort of an important thing to keep in mind, as we'll talk about an interesting feature of pulsars now that we return to that class of object. But we'll get to that interesting feature towards the end. Alright, so let's return to pulsars. Remember, they have typical periods of, say, 0.2 to 1 seconds. And then they have a very slow time rate of change of that period. They have very slow p dot, 10 to the minus 15 seconds per second. And so that is very stable rotators. The longest period for a pulsar known is something like 8.5 seconds. So there's sort of a range of 3.5 orders of magnitude in period that is spanned by sort of all the known pulsars. But it's interesting to note that as we're saying, these guys are spinning down, you can start thinking in terms of, well, if I wait around long enough, one of these pulsars will actually reach a point where it too kind of rotates slowly like the magnetar, and everything shuts off. At that point, we go ahead and say that that pulsar is dead. Now, what happens if I've got a binary companion next to this pulsar? And that binary companion is just a regular star going through the phases of the life cycle of a star. Exactly. Right? This star will eventually, the companion star, will eventually reach some giant phase. It'll puff out. And when it does so, it will overflow its Roche lobe, which is the region that it dominates gravitationally. What that means is all that material that overflows the Roche lobe go ahead and start to form an accretion disk onto this neutron star that is the dead pulsar. Now, if I've got an accretion disk, what does that mean that I'm contributing to the neutron star? I'm contributing mass, and what else? I'm contributing angular momentum. And lastly, yeah, probably some charged particles. So I'm giving it angular momentum, I'm spinning the thing back up a bit, I'm giving it a fresh supply of some charged additional material. I could, in fact, with those charges, because all of this is a plasma, be contributing additional field lines of magnetic field which are frozen into that accretion disk and compacting onto the neutron star. I'm also spinning it up, so I could be reviving some of its own magnetic field, depending on what's going on in that superfluid core. So I can actually revive this neutron star. When I do that, it's recycled into some object which we call a millisecond pulsar, not surprisingly, because its period at that point ends up being milliseconds, right? Because it's been spun up. So in that case, these guys are again very rapid, and they are also very, very stable. Again, in terms of their period, the p dot is now 10 to the minus 19th seconds per second. And there's sort of a nice lifetime tracking or life cycle tracking diagram akin to the way that we can plot stars on the HR diagram. And we understand that on the HR diagram there's these Hayashi tracks for the birth of a star, and then we could plot how they maneuver up to the giant phase, and then even the second giant phase, and all of that, and how they then go off the track. We can do the same sort of thing for these pulsars, just in terms of plotting their period and the time rate of change of their period. So we get something called the PP dot diagram, in which pulsars are born in the upper left, i.e. they're spinning rapidly, so have short period, and spinning rapidly, so they have a sort of larger P dot, because sort of the more you're trying to drag your field lines through the material around you, right, the more it's going to resist and slow you down. So you start off with sort of a large P dot, comparatively, and as you slow down, that dragging effect also decreases, so you kind of move off slowly through evolutionary track of moving down and to the right. Then they kind of disappear into the graveyard, which is sort of at the bottom right of this diagram, because they've spun down and really lost the ability to beam, etc. Then, if they happen to be recycled through this mechanism, they get reborn as the millisecond pulsars, and those are in the lower left. Right, so this PP dot sort of really tells us almost everything we need to know about a pulsar. We can use it to figure out the characteristic age, as we talked about last time. We can use it to figure out where it is in its evolutionary track. We can use it to figure out things about what the magnetic field is doing, etc. So it's quite amazing. These objects are really completely quantified by thinking about just the period and the time rate of change of that period, the stability of that rotation. Right, and here again, just a quick reminder, the characteristic age is period divided by 2 times p dot. And as I said, we'll be talking about the Crab pulsar a lot. So let's think about it. Well, if we put in the values for its period and p dot that are measured, we actually come up with a characteristic age of 1,250 years, which is not bad, because we actually know, because this supernova that actually sort of created this neutron star was recorded by Chinese astronomers in the year 1054. So we know actually how old this guy is. And you see, well, 1250 isn't that far off from the 1,000, well, almost 1,000 years that it actually is. So this characteristic age does quite well in terms of reasonable order of magnitude for the age. And then we can also, as an example, figure out the magnetic field just from measuring PP dot. It turns out to be in this case 4 times 10 to the 8th Tesla. Now the Crub is going to be actually useful for talking about some other features of pulsars. So let's see what some of those are. The first thing is, of course, we've been talking about this all day and last time as well. Pulsar is rotating, it's radiating away energy. Energy has to come from somewhere. Where does it come from? It's coming from the rotational energy of this pulsar. That means this pulsar will slow down. We have this p dot. We understand the relationship between that, and we can figure out sort of what's going on with the pulsar. In the case of the Crab, we find that the time rate of change is 89 nanoseconds per day. So let's think in terms of the actual, what that means in terms of its energy. Where's that energy again coming from? It's rotational energy. So we could easily figure out what that energy is, and then ask the question, does that energy really account for the observed emission of that neutron star, or that pulsar? Well, so let's first figure out what the energy is. Based on all of the observations, we know that the energy for this Crab pulsar, actually the loss of rotational energy, is 3 times 10 to the 31 watts. And you remember that a watt has units which are kilograms meters squared per second cubed, or ergs per second, or energy per unit time. So that's a power. And then we can ask the question, well, how is the neutron star emitting? Or rather, how is the pulsar emitting? Where is this energy going? Hint, we talked about its spectrum having 2 components. What were they? Thermal, which means it's just sitting there and doing what in terms of energy? Radiating as a
black body.
Yep, perfect. So we got black body radiation. So we can easily figure that out because we can model that spectrum, find the temperature, and we know exactly what kind of power is associated with that. And then what else? Yeah, it had that synchrotron energy from its beams. Now we can also, we understand that's a power law spectrum related back to the magnetic field strength. We can also figure out what's going on there in terms of energy and say, is that going to equal this 10 to the 31 sort of watts? What do you think the answer will be? Why? Do you have any idea of what else a pulsar might be doing? Right, losing mass. We already said it's liberating some particles off of its surface through that induced electric field. Some of them go into this beam, and some of them go into a wind. So indeed, we ask that question, is it equal to just the amount radiated as sort of a black body and through this synchrotron emission? No. The energy we just computed is way more than what goes into that sort of emission. So where does it go? It goes into this mass loss transporting material, and it goes through this pulsar wind, which gives rise to a pulsar wind nebula, and that nebula shines at some distance away from the surface of the neutron star, and finally emits that energy. And we can then ask the question of, well, does that then give us the full story? So that nebula eventually actually shines. That's why we know it's there. And we can ask how much energy is coming from that. And indeed, that basically gives us sort of that missing chunk of energy. You see, this is the largest, this nice large chunk of it. It is coming from the luminosity just of the nebula that surrounds the pulsar. Something like 10 to the 30 watts. So a nice, good, 10% chunk of that energy is coming from the nebula, and we understand then that indeed this rotational energy is where all of this emission is coming from. So the nebula, the synchrotron, and the thermal. Alright, so at this point it's worth taking a quick summary of the sort of things that we understand. The observable for a neutron star is its period, time rate of the change of its period, and if you want to get fussy, the time rate of change of the time rate of change of the period, etc. So you could keep going with P double dot and down the line, but most of the properties of a neutron star are well modeled by P dot. Once you've got those two, you can form the characteristic age. You can also figure out the energy, the spin down and luminosity of the neutron star, and you can even figure out what the magnetic field is doing just by using that P dot. So what else is there to say about these pulsars? Well, we just mentioned this wind. So let's think about what's going on with the pulsar wind. Well, the pulsar is, at the very first, sitting at the center of its supernova shock. Right? So we know we have that sort of standard supernova shock propagating outward. That is the outermost shell here. Right, so there's this shock, it's moving out. There's a reverse shock moving back. There's all this shocked material. And we actually have a pulsar wind. Now, like any good sort of wind, that wind eventually has swept off enough of the shocked material left behind by the supernova shock that it kind of slows and you get a termination shock. So you've got these several layers of things happening as this wind, this pulsar wind of the charged particles being liberated, comes off the surface of the neutron star. Here is just another kind of schematic representation of that, and showing you that all that stuff about the sort of light cylinder for the neutron star and the field lines and all of that are just really teeny tiny bits of the overall general state of a pulsar, because we've got this wind which extends much farther out, and outside of that we have the supernova shock. Well, what else can we say about this? There's going to be an evolution of that pulsar wind nebula. Now initially, all we're doing is our neutron star is sitting at the center of this supernova remnant. That supernova shock is propagating outward. It's well removed from everything that's going on with this pulsar. And that supernova shock has gone through and left a fairly low density shocked material behind. So initially our wind is basically kind of moving through nothing. It's picking up mass as it goes, but not much. So it's basically undergoing free expansion. Particles stream off, and they don't have to do much. They sweep up and they shock the surrounding ejecta into a thin shell at the edge of this nebula, but it's not very much mass. And another way of saying it is the pulsar wind nebula shock velocity is much larger than this sort of neutron star velocity. So the wind is free to move with the neutron star inside the supernova remnant, i.e. everything stays kind of nicely centered. So everything moves kind of initially kind of nicely together, but then actually what happens, sort of thinking about the supernova remnant shock, well, that's already reached material that's kind of slowing it down compared to that initial explosion. There's this reverse shock and everything's going like that, which means the pulsar wind nebula is centered on the supernova remnant, this neutron star. Those go together, but the supernova shock is sort of separate now because it's moving slowly. So those two actually move within the supernova shock after a while. And so you lose that center of motion. And it'll not be too surprising that we get a variety of kind of pulsar wind nebulae, what they look like. There's some examples here. You can have nicely ordered ones in this kind of disk, or you can have sort of chaotic ones that kind of look all over the place. But what's going on is initially this free expansion, which allows them to kind of move the pulsar wind nebula and the supernova remnant, i.e. the neutron star, together, and they move kind of freely inside that bubble of the supernova shock. But then, what happens? Well, if you let time go long enough, the pulsar wind will eventually reach the reverse shock coming from that original supernova explosion, from the fact that that has now finally, swept up enough mass that it's slowed down and has sent this reverse shock moving back towards the material, towards the center of that supernova remnant, or nebula. And that material is now dense, right, because it's coming from this reverse shock. At that point, it's not going to do any more free expansion, because now it's sweeping up in quite a bit of material, and it's meeting this reverse shock, just trying to drive it back. Right, so it is no longer in this kind of pressureless environment where it was just sweeping up a little bit of mass. It's now sweeping up much more. So initially, what you have is the pressure behind the reverse shock is higher than the pressure inside the pulsar wind nebula, which means that the pulsar wind nebula is compressed on that side that's meeting the reverse shock. So it's going to be deformed. As it contracts, that pulsar wind nebula pressure will obviously increase, and then it will end up being higher than the pressure of the exterior, and it will be able to re-expand inside that supernova shock region. So what's that going to do? It means that the expansion velocity overall is going to decrease for the pulsar wind nebula, and now it's sort of going to lag behind what the neutron star is doing. Because the neutron star, right, is sitting at the center of the pulsar wind nebula, it doesn't know that the pulsar wind nebula has encountered the shock and been compressed and all of that. So now they're not going to be centered on the same point. The neutron star will seem to drift inside its pulsar wind nebula. So it's going to be detached from that pulsar wind nebula that it's so far created. And you end up with something that looks like that, basically. Right, so you sort of have ISM, shocked ISM, inside this supernova shock. You have a nice termination shock from where your wind is encountering that ISM, and you get sort of this region of the shocked wind. This guy inside is still doing free expansion. It doesn't care about this this side of it reaching the sort of reverse shock. And so we have this kind of diagram where now the neutron star is moving through its pulsar wind nebula with its original speed, because it doesn't yet know about reaching the reverse shock. But the pulsar wind nebula is distorted. And indeed we see stuff like that, where we have this nice kind of bow shock and these shocked wind trailing behind the neutron star. So then, what can happen? Well, we're talking about this pulsar wind nebula. It's going to detach from its original, the neutron star is going to detach from the original pulsar wind nebula, and then there's sort of two things that happen. That detached pulsar wind nebula is sort of stuck and continues to do this contraction and re-expansion to try to drive against the thermal, the reverse shock. And it's going to just try to achieve some sort of equilibrium with its surroundings and kind of blend in with that reverse shocked material. That process lasts some thousands of years. But in the meantime, what is the neutron star doing? What do you think? it's still continuing its life. So it's going to go ahead and do what? Yeah, it sort of keeps creating sort of a new nebula. So there's a new pulsar wind nebula that initially expands subsonically, and then as you reach this supernova remnant shell, its velocity becomes supersonic compared to the surrounding material. That also will then get shocked, and you get the same sort of thing as in the previous example. And then, what happens? Well, then the neutron star finally realizes that it's at the shock. It can actually leave because it passes through. It's got, a big chunk of mass. It doesn't matter that it's kind of sweeping up some of this material. It can pass through that shocked material, and it can leave that supernova remnant shell. It's still emitting during this wind. That's going to energize that bit of the shell, of the shocked material, and then it's sort of going to be free. And so you can actually see, or imagine at least, cases where you have sort of a nice supernova nebula happening without a neutron star anymore anywhere in it. Alright, so that's the generic story of how these things evolve, and we will take a break and then come back and do the tooth bit.